Okay, I'm going to go over the answers to the stoichiometry test. To show you how I did it, and what the right answers are, and just maybe more to help you understand what's going on. So the tests were kind of all over the board. Some people got it, some need help, and I thought this might be. And also, you get to see what the answers are compared to what you think you got. So the first problem says, how many grams of solid iron 3 hydroxide will precipitate when 100 mils, 0.3 molar sodium hydroxide, so aqueous solution, is added to 200 mils of 0.25 molar iron 3 nitrate, also aqueous solution. All right. So here's the balanced equation. Okay. This is a double replacement reaction. So what we're doing is we're taking this solution here and combining it with the sodium hydroxide solution. And when you mix them together, what they do is they produce a solid. And this is the solid. And I want to find out how much of this I added. So the states I have here is I have solutions. Okay. And solutions. Okay. And then this is a solid. Okay. All right. So since I have more than one reactant, I need to find out which one of these is limiting. But first, what I need to do is to do that. So I need to find out which one's limiting. I have to figure out how many moles of each there are. Since I'm using solutions, I'll be using molarity. Okay. All right. So the sodium hydroxide. So first of all, turn the mils into liters divided by 1,000. So I have 0.1 liters of sodium hydroxide, and it's 0.3 moles per liter. That's molarity. Mole per liter is molarity. And then, if you notice, the liters cancel out, and you end up with moles sodium hydroxide. Okay, the iron nitrate is also a solution, so you can use molarity again. Here's the volume times the molarity, and it'll give you this many moles of iron nitrate. So, just quick, number of moles is going to equal the molarity times the volume, okay, or big M times V. All right. So we have our moles. Now we need to find out limiting, and so what we do is here's our recipe table, and then you put both of them in. There's slots. And then you find out how many you can do with how many recipes you can do with each. So if you have 0.05 moles of iron nitrate, you can do the reaction 0.05 divided by 1. And if you have 0.03 moles of sodium hydroxide, you can do the reaction 0.01 times. Okay. All right. So here you can only do a 0.01. Here you can do a 0.05. So obviously you're going to run out of the sodium hydroxide before the iron nitrate. You can see that there's 5 times as much iron nitrate. So then sodium hydroxide. So you're going to use all this up, and you'll have more than enough of this left over. So this is going to determine how much product you make. So you put that number over here. Right, and then you figure out how many moles that is. So you just multiply by the moles recipe. And this is how many moles of iron hydroxide you're going to form. All right. Okay, so the question says it wants solid iron. So whenever you have a solid, you'll be using molar mass. Okay, so we're going to multiply by the molar mass. And so go from when you have moles to grams, you multiply by the molar mass. Okay. And that's because, like, if you have 1 mole of, for instance, this one, 1 mole is 106.9 grams. If you have 1 mole, it's 106.9. If you have 2, it's going to be twice that amount, or 2 times. Okay, so we have 0.01 moles times 106.9, and when you do that, you see that those cancel out. You may want to put these in parentheses just so it doesn't get confusing. And then you end up with grams of iron hydroxide. So there's your problem. The answer. Okay. So you'll see this as a theme. What you have take, if you have more than one of the reactants, more than one reactants, you're going to find the limiting. But first of all, you have to find the moles of each, and then you plug them into the table. Figure out which ones will give you the least amount of recipes. Okay, then figure out how many moles of the products you need or whatever you're asked for, and then find it. Remember using states. Okay, if you have the solids, you'll be using molar mass. Okay, if you're using a gas, you'll be using PV equals nRT. If you're using molarity or solutions, you're going to use molarity. And if you're using liquids, pure liquids, then you're going to be using both molar mass and density. So keep those in mind when you do these, okay? I know the test is over, but it's nice to be able to walk away with how to be able to do it. Second problem steps. So what volume of 0.2 molar sulfuric acid, which is a solution, is required to neutralize 75 mils of 0.3 sodium hydroxide? So here's the balance equation. If you notice, it's an acid-base reaction. So when you say neutralize, you have the acid, which is sulfuric acid, and it's and you're neutralizing the base. Okay. So you're only given one of the reactants, and the reactant you're given is sodium hydroxide. Okay. And what you want to do is you want to find out the amount of the other reactant. Okay. All right. So we don't have to find a limiting because we only have one of the reactants. This guy right here. Okay. So what we can do is immediately put it. So what we need to do is find out how many moles we have. So this is a solution. So this is a solution. So use molarity, 0.075 divided by 1,000 to get liters, times the molarity. Okay, when you do that, that cancels out. And you end up with 0.0225 moles of sodium hydroxide. So that goes right here. Okay, and then what you do is find out how many recipes you can do it. So you can do the recipe, so divide the 0.0225 by 2 and do that. Okay, so then bring that number over here. So you're doing the recipe 0.0113. How many moles is that? Okay, multiply by 1. So you're going to have 1 mole. You need 1 mole of the sulfuric acid to neutralize 0.0225 moles. All right, so what I want to do is find the volume. Okay, so I'm going to use molarity. I have the molarity, and I want to find the volume. So I have moles, and I have the molarity right here. Okay, so this one, so here's moles. Okay, now what you can either divide by the molarity, or you can do it like in dimensional analysis. So just flip the molarity, so 1 liter over 0.2 molar. Okay, and the moles cancel out, end up with liters, and it's 0.05625 liters. Divide that by 1,000 to get milliliters. So it's 56.25 mils of sulfuric acid. So what this says, you need 56.25 mLs of 0.2 molar sulfuric acid to balance out 75 mils of 0.3 molar sodium hydroxide. There's kind of a cool little quick formula you can actually use to figure this out, but this is actually a good way to do it because it tells you actually what you're actually figuring out what you need to do. You need to find out moles and then figure out what you need. So key is always find moles, and then recipes, and then out of that moles again, and then figure out whatever you need. Okay, number 3, how many liters of hydrogen gas will be formed when 3.50 grams of solid zinc are added to 100.0 mils of 2 molar HCl? Okay, the balanced equation. And this is a single replacement reaction using an acid. We're given more than one reactant. We're given both its amount of zinc and we're given the amount HCl, so we have to find out which one is limiting. So we're going to have to figure out their moles and then plug them into the table to figure out that which one's limiting, and then from there we can figure out moles or product and figure out how much product we need. Okay, so find the moles of each reactant. So the moles zinc is a solid, so we're going to use molar mass. So we have 3.5 grams divided by the molar mass, okay? Or you could write it as this, like a dimensional analysis. Either way, you get the same answer. So you have, 3.5 grams is the same as 0.0535 moles of zinc. All right, so I'm going to put that number right here. I rounded it. And then how many moles of HCl do I have? It's a solution, so I'm going to use molarity. So change it to liters, 0.1 liters times 2 moles per liter. The liters cancel out, and you end up with 0.2 moles of HCl. Okay, then what you do is you put them in a table and you find out how many recipes you can do using either. So the 0.054 moles would do the reaction 0.054 times. Okay, if you, while it's hydrochloric acid, you have 0.2 moles, and you can do the reaction 0.1 times. Okay, so you can see that you have a whole lot more hydrochloric acid than zinc, and so this is your limiting. Okay, so bring that over here. So your limiting determines your product. So this is how many times you can do the reaction. Now figure out how many moles that is, so multiply by the moles per recipe. And then you have 0.054 moles of H2. Okay, now so how much, so what, from that we can figure out the amount of product. So I want to find hydrogen gas, liters. Okay, so I'm going to use ideal gas law. And solve for V. Okay, so rearrange it, so PV equals nRT, rearrange for V, so V equals nRT over P. I told you temperature is 298, or 25 degrees Celsius, and the pressure is 1 atmosphere. And R is 0.0821, so we'll put all those numbers in. So I have 0.054 moles times R times temperature divided by pressure. Okay, so if let's take a look at the units, you can see that these units cancel out, these units cancel out, and atmospheres divided by answers cancel out, so end up with liters. Then multiply everything out. 0.054 times 0.821 times 298 divided by 1, and your answer is 1.31 liters of hydrogen gas are produced in this reaction. Okay, number 4. How many grams of solid copper will form when you have 8 grams of solid magnesium and added to 150 mils of 2.1 molar copper sulfate? Here's the balanced equation. You have more than one reactant, so we're going to have to find limiting. But for that, you need to find out moles, and then you can pick that and put it in the table to figure out limiting. So the moles of magnesium, okay, it's a solid, so you're going to be using molar mass. So 8 grams divided by the molar mass, 24.3. And it's okay, and then you end up with moles of 0.329 moles of magnesium. All right, okay, and I'll round that to 0.33. Okay, moles of copper sulfate, that's a solution, so I'll be using molarity. So 100, actually that's wrong, 100, so I have 150 is 0.15 liters times molarity 2.1 moles per liter, and that's 0.315 moles of my copper sulfate. Okay, put those down here. Okay, and then figure out how many recipes you can do for each. Okay, and you can see this is the least amount of recipes. So this is going to determine how much product you're going to make. Okay, so you can do the recipe 0.315. Each time you do it, you need 1. Okay, so 0.315 times 1. So you're going to make 0.315 moles of copper. Okay. All right. It says I want to have in grams, so I'm going to use molar mass. So I take multiply by the molar mass of copper, which is 65.55. So it's 0.315 moles times 65.55 grams per mole, and it ends up with 20 grams of copper. Okay, so this question is how many liters of carbon dioxide will be formed when you have 8 liters of methane combined with 850 liters of oxygen gas, and also how many mils of water will be formed, liquid water, when it has density 1 gram per mil. So here's the balanced equation. Okay, so we have more than one reactant, so we need to find limiting. But before we do that, we need to figure out the moles. Okay, moles of methane, so it's a gas, so we're going to use the ideal gas law. PV equals nRT, so for N, so N equals PV over RT. So N is going to be 1 atmosphere. P, volume is 8 liters divided by 0.0821, and divided by 298, and you end up with 0.326 moles of methane. The moles of oxygen, again, it's gas, so you can use PV equals nRT. Okay, same arrangement, and you get 2.04 moles of oxygen. Okay, put them in their respective places. Figure out recipes. Okay, so you can do the recipe with the methane 0.326, and with the oxygen you can do recipe 1.02 times. So this is the lower amount of recipes you can do, so that's going to determine the amount of product. Okay, so that's how many recipes you can do total. So now figure out how many moles of each. Okay, so 0.326 times 1 and 0.036 times 2 gives you associated numbers. Okay, now we can figure out the amount of product. So first thing we're going to do is says how many liters of carbon dioxide. So it's a gas, so we're going to use the ideal gas law and want to rearrange itself for V. Okay, so V equals nRT over P. So I put in 0.326 right here times R times T divided by P, and I get 7.98 liters of carbon dioxide gas. Now for the water, okay, it's a liquid. Okay, so I'm going to use density and molar mass. So the first thing you need to do is find out how many grams, and then you can figure out density from that. So you have 0.652 moles times 18 grams per mole. And so you have 11.74 grams of water. Okay, each mil weighs 1 gram per mil, okay, or 1 mil weighs 1 gram. Okay, and then you end up with 11.74 mils of liquid water. Okay, notice the theme here. Okay, the theme is if you have more than one reactant, well, you always need to find moles, and then if you have more than one reactant, you need to find out which one is going to give you the least amount recipes, and then determine how much product you make, moles of product, and then from moles of product you figure out whatever we measure, solid, liquid, concentration, or gas. Okay, last problem. How many milliliters of liquid pentane with a density of 0.75 grams per mil are needed to form 300 liters of carbon dioxide gas when you have oxygen in excess? Okay, so here's balanced equation. We only have one reactant. Okay, we're told that the oxygen's excess, so we have 300 liters. No, we we only want to find one of these guys. Okay, so we're only given one thing. We're only given the amount of carbon dioxide, so we don't have to find limiting. So when you're only given one thing, and usually, whenever you're given product, you'll be usually given just one of the things. So you're given 300 that we produce 300 liters of carbon dioxide, and this is at 1 atmosphere, 298 Kelvin. Okay, so we want to figure out how many moles of carbon dioxide is. We're going to use ideal gas law, plug everything in, and you end up with 12.26 moles of carbon dioxide. Okay, put that number right here, then figure out how many recipes you can do with it. Okay, all right. So you can do it 2.45 times. So you have to do it 2.45 times to make 12.26 moles of carbon dioxide. Okay, so how many moles of pentane is that? Well, every time you do it, you need 1. So if you do it 2.4 times, you need 2.4 times. And so that's going to give you 2.45 moles of pentane. Okay, now from there, you need to figure out mils of liquid. So we're going to use this number to figure out the mass. And then from that, we're going to take density to figure out milliliters. Okay, so to figure out the grams of pentane, we take the moles times the molar mass, and you get 176.4 grams of pentane. Okay, the density is 1 gram per 0.7 grams per mil. Okay, and you can do this different ways. You can take this and divide it by the density, or you can set up in dimensional analysis. So it'll be 176.4 grams times. So we can flip this so that grams will cancel out. All right, and then you end up with 235.2 mils of liquid pentane. Okay, when you combust that, okay, it's going to produce 300 liters of carbon dioxide at 1 atmosphere and 298 Kelvin. Okay, so there you go. There's a set of problems. I hope that helps you out. Okay, got any questions? Let me know.